moving on to a different topic. We have the comparison test. Okay, so the comparison test, well, this is specifically for improper integrals, since we're in that section, improper integrals. Okay, so what this says, I'm just going to write it down and then I'll explain it. So we're assuming that some function, f of x, is greater than or equal to g of x, which then is also greater than or equal to 0. Okay, so what this means, and this 0 here, that means that some function, so like a y equals 0, so that would just be the x-axis, right? So this is going to be, here's x and here's y equals 0, right here. Okay, so what this means, basically this part right here, just means that f of x and g of x all stay above the x-axis. Okay, they're all positive. So these are positive functions. Positive functions. Okay? Alright, so we have two cases that we can build off of. From this assumption, I guess. And we also, well, we're also thinking, this is a given thing as well. X is greater than or equal to a. So you'll see how this plays in once we start applying it. So we have case number 1. Case 1. Alright, so this is if, then we have our integral x to the a to infinity, sorry. So this means the same thing as x is greater than or equal to a. That just means that we're starting at a, some a, could be 1, 2, 3, 0, whatever. And then we're moving all the way to infinity, going to the right. Okay? So case 1 says, if the integral from a to infinity of f of x dx converges, and remember converges means the limit exists, then, this is the second part, then a integral of, from a to infinity of g of x dx must also converge. Okay, so what this means is basically, I'm just going to draw a little diagram. So let's say we have, alright, that was a bad line, but let's just go with it here. So we have our x and our y, and let's say f of x is something that looks like this, right? And then our g of x, which is also positive. Both of these are positive functions because they stay above the x-axis. So the top one here, top, is f of x, and our bottom one here is g of x. Okay, so this is what the assumption is basically saying. So f of x is greater than or equal to g of x. So f of x, the value of it, so the y value is always above g of x at any given x. Okay, so this is what our graph looks like, and then we're taking the integral from a, let's say a is here. A could also be on the left side of 0, it doesn't really matter. You just have to set an a, or the problem will give it to you. So from a to infinity, so going that way. Alright, so everything on the right of this line, that's what we're looking at. And so the second, so case 1 is saying if the integral from a to infinity of f of x dx converges, then g of x must also converge. So what I like to do is kind of think of the comparison test as, well, another name for it is like squeeze theorem or squeeze test, whatever you want to call it, because basically the g of x is kind of like in the middle of the sandwich. The x-axis, it can't go below the x-axis because these functions have to stay positive. Stay positive, that's funny. Maybe they're really optimistic or something. And then f of x is always supposed to be above g of x, right? So if f of x is as it goes down, 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 and it's going closer and closer to the x-axis, so must g of x, right? So if we look at it in the long term, let's say f of x is getting closer and closer and closer, and then g of x has to stay underneath and right in between. So if f of x converges, so must g of x. Okay? And then, now we're going to do the opposite case. So case number 2, this one says, if, well, I'll do a colon and look all fancy. Okay, so if integral from a to infinity of g of x now diverges, then so must, and then we're going to have the other integral from a to infinity f of x dx. Okay, so I'll draw a little diagram for this as well. So now we have something that looks like, now instead of, well, g of x is going to diverge, so that means it's not going down near approaching the x-axis, but instead let's say g of x goes up like that, like an exponential function. So this is g of x. Okay, so it's going to diverge in the long run as x goes to infinity. And then f of x, as our assumption says, it has to be greater than g of x for all x. So f of x is above it somewhere. So this is our f of x. Okay, and then these, again, they're both positive functions, so they have to stay on the top half of the plane. Okay, so what this case 2 is saying is that as g of x, if the integral diverges, then so must f of x, because, and again, this is kind of like a sandwich thing, where g of x, if it goes up indefinitely and it continues to go up and up and up, and then f of x, because it's greater than it, it must always stay above the g of x line. Okay, so even if g of x is going up, then f of x has to go up with it. All right? So it's kind of like pushing it up. Okay, so let's do an example of this. Quick example. So we have integral from 1 to infinity. So in this case, a equals 1, right? And then we're given d of x, or dx, sorry, over x to the third plus x. Okay, so we're asked whether this, we don't need to evaluate it, but we need to figure out whether this converges or diverges. So does this exist or not? The limit, does the limit exist or not? So in all the comparison test problems, the basic concept behind it is just that your given function here, so our 1 over x to the third plus x, square root, that is your g of x. Okay, that's the thing that you're trying to squeeze in between 0, again, this means the x-axis, and so this is our middle function kind of thing. So what we need to do is come up with some f of x that is always greater than g of x, and then we need to prove something about it. So yeah, okay. All right, so we need an f of x that's either greater than this g of x, yeah. So let's say we have, well, just as like a basis, I'll write a little hint here. When your numerators, when numerators are equal, and let's see, when numerators are equal, the function with smaller denominator, and I'm just going to abbreviate denominator, is the bigger function overall, right? And then this makes sense. So, okay. So I'll compare on the next slide. We'll come up with an f of x, okay? So this is what we have. Yeah. Right now we have x to the third plus x all under a square root. So we want to know this is less than or equal to what? And this is what I'm going to propose, is that this is less than or equal to 1 over x to the 3 over 2. Okay, and this is the same thing as 1 over square root of x to the third, right? And we know that x is always going to be, well, given our integral in the beginning, our left bound, or our lower bound is 1, so, and it can only go to the right from there, so x's are going to remain positive, so that's good. And so basically, this is true because the bottom, the denominator, well, first of all, the numerators are equal, they're both 1, right, on both sides. And then the denominator on the left is always going to be less than or equal to the denominator on the right, right? Okay, let me rephrase that. The denominator here x third plus x is actually going to be bigger than or equal to the bottom over here on the right, correct? So then once we flip them, you know how, well, I guess this is kind of like algebra, but when you do both sides to the -1 power, both sides to -1 power, you have to flip the sign in the middle, the inequality. So we actually get this, right? 1 over that, which is what I said in the beginning. So this is our f of x they're going to be comparing it to. Okay? So now let's set up the integrals. Well, yeah, okay. I'll set it up on the next one. Okay, so on the left, we have our 0, which is y equals 0, basically, which is the x-axis. And then we have our g of x in the middle here, which is equal to 1 over x to the third, or square root of x to the third plus x, which is less than or equal to our f of x, which is 1 over this, right? Okay, so we know that 0 is, okay, so this is like y equals 0, and this is always going to converge automatically to 0, so that's kind of a given, all right? So the left side's taken care of, and then the right side over here, we need to know, so this converges, yes, yay, okay. So then on the right here, we need to figure out whether this converges or diverges. If it converges, then we're good, and we can say the middle one converges as well, because it's being squeezed by both the left and the right, okay? But if the upper limit, or if the upper function, f of x, were to diverge, okay, so let's say we have a g of x and an f of x, so f of x is on top, right, because it's greater, and g of x is here. If we somehow were to figure out that f of x diverges, that tells us nothing about g of x, right? Because we can't predict that it's going to diverge as well or go closer to the x-axis or anything. So basically we're aiming for converge here for f of x. Okay, so let's apply the p integral test. So our interval for the integral was 1 goes to infinity, right? So and we can tell that p on the bottom here, so this is the same thing as 1 over x to the 3 over 2. So p equals 3 over 2, that's our power, and this is greater than 1, right? So this is going to converge by the, I don't know if it was a theorem or a definition, one of the things I gave in the earlier slides, and you can also find it in your book. So basically this is going to converge, which is good, because if both sides converge around g of x, that means that this must also converge. So g of x must converge. Okay, all right, so that might, I mean, the comparison test, it does take some experience, and once you do more problems, you'll become more familiar with seeing certain patterns and what are easy comparisons to make. Yeah. All right.